Hi, welcome to my presentation on privacy preserving state estimation with crowd sensors and information theoretic perspective. I'm Farokhi, and I'm a senior lecturer at the University of Melbourne. Our interest in crowd sensing is because these systems are becoming more and more prevalent during our daily life. There is a lot of crowd sensing applications out there. You might have used, Google Maps and so forth. That's a form of crowd sensing that enables you to be able to get accurate measurements of the traffic flow throughout the day, to be able to use that for, optimum, routing, to be able to get to your destination as quick as possible. But there are many, many applications of this out there. For instance, University of Melbourne, there was a time that they used to passively monitor movements of the students through the campus for infrastructure optimization and management by following them through the Wi-Fi network and so forth. The examples are many. There are examples for temperature measurements and air quality control and measurements and quality of service and so forth. Crowd sensing enables us to be able to have a accurate estimation of some important variables in the system with minimal investment through the users of the system. The users of the system would be able to use the smart devices to log reports about, situations that you're in. That would be, if they're actively trying to pass the information to the server, or passively they can send information by letting the server to use the devices as a sensing unit and be able to take measurements based on it. Now, it's wonderful that we can be able to measure important variables, but at the same time, this comes at the cost of privacy implications, information leakage that we should be dealing with to be able to make sure that the users of these services are protected as much as possible. Examples of this are again quite a lot. One interesting international example was when Strava, this app that's used for tracking exercises, cycling and running and so forth, generated this aggregate map of its users across the globe, and that resulted in leakage of some important military information from the US, which was quite embarrassing for the service provider. And also, another example that's more closer to home is when the company that runs the trams in Melbourne decided to publish, uses of trams by de-anonymizing the data sets and passing it to public. But that resulted in also, privacy implications that were quite dire, and they had to take the data off. So we're trying to answer these kind of questions in the context of state estimation, at least using, tools from information theory. So, to be able to answer concretely these problems, we need to make a few assumptions and, present the model that we're considering in this paper. We are going to consider a situation in which the state or the variable that we want to, measure and estimate evolves across time using these linear dynamical equations. X is the state that we want to estimate. For instance, the traffic flow across various, roads in the city, and of course this state kind of remains relatively smooth over time because the state at the time k plus 1, it relates to the state k using the dynamics of the system. The cars don't disappear from the network, so we know that there is a form of continuity, that if the traffic is high now, then the traffic is going to be high a little bit afterwards as well too. But there is also unmodeled aspects of the system that we lump together and represent using this WK, which is the process noise that we would having entering into the system. So if this process noise was not there and we had the estimate of the traffic at any given time, we would be able to forecast it for all of the future. But that's not really true, because there's always unmodeled behaviors and properties that go into the system, and we need to keep track of this state measurements and be able to estimate this state over time. In this paper, we're going to assume this WK is Gaussian because it's amenable to theoretical analysis. When you put non-Gaussian noise, you would be able to follow the framework that we have in this paper, but it would make it a lot harder to be able to explicitly compute things, and then we have to follow a numerical approach to solving the problem. So at any given time, we assume that one sensor from a pool of M sensors that are potentially more than one, and those are our crowd, is randomly selected, you know, and this sensor would be able to give us a linear measurement of the estate. This measurement is captured using the CI times X. So we're getting some of those X's or a combination of a few of them together. And there's also measurement noise signified by this VI. And this measurement noise again is something that would filter out and goes into the state. And various sensors have different models, so they would have different C's potentially, and also they have different accuracies, so they have different measurement noise magnitude and so forth. The identity of the sensor, which one of these sensors from 1 to M has been selected at a given time, is given to us using this random variable sk. And we assume that the adversary doesn't know this random variable sk, and the adversary wants to estimate and guess this to be able to figure out which sensor was used from the crowd to construct these state estimates that we have. So the job that we have in this paper is trying to understand, how successful is the adversary to try to capture this SK, this random variable, and how we can make this harder for adversary through adding, randomization and noise to our, state estimates and so forth. So, of course, the selection of the sensors in real life might not be, random. It could be that we specifically seek sensors in the areas that we have less measurements. But this randomness of sensor selection enables us to be able to use information-theoretic tools to estimate what sensor has been used. The randomness enables us to be able to use tools such as entropy, such as mutual information, to be able to construct this. Construct measures of privacy and be able to analyze. Now, these sensor measurements are used by a system operator to construct the state estimate, and we assume that a Lowenberger-like state estimator, these estimators are very frequently used in control systems and signal processing society to be able to construct estimates of the states of the system that evolves with time. So you update the estimates based on the model of the system. Notice that this A is the same as the model of the system. And then you have an adjustment term based on the output that you have received to be able to compensate for the errors over time. Now, typically in these Lowenberger state estimators, there is no additional noise term, this KC that we have here added in, because we are interested in constructing the best estimate. Now, in this paper, we are having this KC term here, this noise that we can add into the estate as a measure, as a way to be able to preserve privacy. That enables us to be able to ensure privacy. And in this paper, we are going to look in the effect of this noise on the privacy. If we crank up this noise, we can make information a lot more private, but that comes at the cost of getting worse state estimates. And the state estimates are shown by this X hat that evolve over time, and they are released publicly. So we want the adversaries or malicious agents out there to not be able to use this X hat to identify what sensors has been used to generate this X hat. So the identity of the sensors, this SK, we want to remain hidden. As I said, our goal is to understand would an adversary be able to infer the identity of the sensors based on the state estimate or potentially some other side channel information? The adversary may know the dynamics of the system, may know the actual states of the system, might have sensors of itself embedded in the system to be able to reverse engineer these state estimates and figure out the identity of the sensors used. That would be a very strong adversary. If we can analyze this strong adversary, we'll be able to also understand the behavior of the less strong adversary, because the stronger adversary provides an upper bound for the amount of information that leaked to a more ignorant adversaries. To be able to understand private information leakage, we use mutual information. Mutual information is a measure of information that's proposed in information theory for analyzing capacity of communication channels, and essentially shows how much two random variables are related to each other, depending on each other statistically. So we are interested in understanding the mutual information between the identity of the sensors and the state estimate X hat. If this information is quite large, it means the adversary has an easier time to understand what or estimate what is the identity of the sensors is. If this information is lower, the life would be a lot harder for adversary. The motivation behind using mutual information is a fairness inequality that enables us to be able to show if an adversary is trying to guess, estimate the identity of the sensor's SK, the quality of that or the probability of correct detection relates to the mutual information and conditional entropy of this variable. So this is rooted in information theory, and there is a lot of interesting literature out there that use mutual information and conditional mutual information as measures of information leakage in privacy analysis. And there has been a lot of literature out there trying to show that these measures are good, and when they are good, when they are bad, and can we use them to understand privacy in machine learning, privacy in dynamical systems as in here, and so forth. Now, an aggressive adversary, in addition to knowing X hat, might also know the X, which is our underlying variable we're trying to guess. So this is an adversary that's very proactive. It goes out there trying to measure the estimate, understand what the state X is directly, and then use that to try to figure out what are the information that's leaked about the identity of the sensor. This is a very strong adversary. So if we can understand, analyze the behavior of this adversary, we would also be able to bound the behavior of the adversaries that don't have access to this XK. Okay, so additionally, information available to XK makes, to the adversary makes it easier for them to be able to identify the identity of the sensors. So a privacy metric is the measure of this information between identity of the sensors, S, and estimate of the state, X hat, condition on the adversary knowing what the state is. And we divide this by k and let k go to infinity, because as k grows larger and larger, the vectors of this random variable grow larger and the information content grow larger. But we want to understand what's the average information leakage about the identity of the sensors. So we are going to assume that the estimator that we construct, that Lowenberg type estimator that we showed earlier, is stable. If it's not stable, it means that the error of it can potentially go to infinity, and that's not really a good estimator. So this is not really a drastic assumption, because otherwise, what's the point of releasing this data information or estimate that potentially has a very large error? Nobody's going to use it. So we're going to assume that this error is bounded. We're not going to assume that it's a small or anything. We're just going to assume that it remains bounded. So in the paper, and I don't put it in the slides here because it would have made these slides quite ugly, there is an explicit upper bound for this measure of information leakage that we had in the previous slide, based on the parameters of the sensor and the magnitude of that privacy preserving noise that we show with this uppercase K. So this noise growing larger would potentially be able to allow us to have more privacy by making this measure of information leakage becoming smaller. Essentially, we use this upper bound showing that information is always positive, greater than or equal to 0. With making this Kc, the magnitude of the noise, the variance of the noise larger and larger and larger, we can reduce this information leakage and make it smaller and smaller and smaller. We can push it to 0. So this essentially shows us that for any level of privacy that you want to guarantee, if you want to make this measure of information leakage to be smaller than epsilon, we can always find the noise that would ensure that. So this shows that the mechanism that we are proposing is a useful mechanism because it enables us to be able to achieve the level of privacy that we are interested in. We can achieve whatever we want. So that's quite a powerful result. We can ensure any level of privacy. But unfortunately, something else that happens is that when you make the noise in this estimator larger and larger, the quality of estimator becomes worse and worse. So there is an inherent trade-off between privacy and utility that we're trying to show to you in the next few slides using a numerical example. So let's consider a simulation setup. We have a temperature estimation problem. We have two side-by-side rooms. These rooms are coupled to each other and coupled to the environment. And the dynamics of them governed by linear sets of equations that you can look into the paper and trying to see the equations. We assume that we have two sensors. Both of them can measure the temperature in room number 1. And one of the sensors is a lot noisier than the second sensor. And if we are using a lot noisier sensor, then the state estimate is going to be a lot noisier. So you would expect to be able to identify the noisy sensor being used using some kind of thresholding strategy. So we use this attack strategy by the adversary that we say, if the measurements that they received from the sensor and the measurements that comes from the state estimate are differ from each other using this equation showing to you below by a threshold tau, then the noisy sensor was used. Otherwise, the less noisy sensor was used. So this is a very simple strategy that the adversary can use without even knowing anything about the dynamics of the plant, which is the two room, the size of the rooms, the material that's used for constructing the rooms and so forth. So they don't need to know any of this to be able to construct this very rudimentary attack strategy to identify which sensor was used. And interestingly, you can see that this very simplistic policy can, give you the correct identity of the sensor nearly two-thirds of the time. So this is a very simple attack. It doesn't require a lot of knowledge. It doesn't use a lot of information to construct the attack. And it's successful two-thirds of the time. It shows you that why, we need to be mindful of this privacy infringing, crowd sensing systems and be able to, secure them. Now, this can also show you that, the value of tau, which is our threshold, can be selected around, zero point 0.1, and that enables us to get, that two-third, performance that we see in this example. Now, let's see what would happen when we increase the amount of the noise that goes through the system. So when we increase the amount of the noise, guessing the identity of the sensor gets harder. You can see that the probability of correctly guessing the identity of the sensor drops as the magnitude of the noise gets larger. Note that this probability at the end converges to half. The reason for it is that we have two sensors and we can always randomly guess. And randomly guessing without anything, just purely blindfolded, sensor one, sensor two, that would give us 50% accuracy. So you would not go below that 50% accuracy. But you can see that we drop from that two-thirds, which is quite significant, to that 50% quite rapidly by adding noise to our system. Now comes the trade-off, because you can see as the amount of the noise, the magnitude of the noise grows larger and larger, the state estimation grows worse and worse, and we would have a harder time trying to construct an estimator that has a low error. You can see that the error of the estimation grows quite rapidly, particularly around this magnitude 10 to the power of minus 2 when the noise passes that. And this is the variance of the noise. And also the error is really dropping rapidly around that 10 to the power of minus 2 standard, a variance. So you can see that there is this nice, tight relationship between your ability to be able to distinguish the sensors used and also the estimation accuracy of the adversary, estimation accuracy of our state. So this shows you the privacy utility trade-off. Now, how good is the upper bound that I earlier told you about? Is that upper bound that we construct in the paper very off, very bad? Does it follow similar trends as this numerical results? Now let's look at the upper bound and this empirically computed ability of the adversary to detect which sensor is being used. As you can see, these two graphs are very similar to each other. They remain constant for the same kind of parameter regimes. They also drop during the same parameter regimes and so forth. The only difference between them is that the top one is measured in bits. So it's different kind of quantity than the bottom one, which is the probability. It comes up as an answer that's between half and 1, while the upper one is a bits. Relates to logarithms of probabilities and so forth. So that have different scales, but nonetheless they have very similar shapes. That's potentially shows that our scheme is, our derivations are relatively tight, and even in this very simplistic adversary can achieve, that upper bound that we have in the paper. Now, to conclude, this paper, we really put forward a, conditional mutual information measure for privacy, particularly in the case of crowd sensing. This is a dynamical system. The state evolves over time. The sensors that are being used changes over time. and using this conditional mutual information averaged over time as a measure of privacy. This enables us to be able to analyze the effect of privacy preserving noise in our estimators theoretically and then demonstrate them numerically using simulations. Now, as future steps for the work, we certainly would like to move towards experimentally verifying these results. Can we use, two sensors? They measure different aspects, or they are, various amount of noise on them, and be able to use similar, framework as we used in the simulation setup to be able to experimentally validate. Would we be able to identify the identity of the sensors if there is no privacy preserving noise? As we add noise, this identification, does it become harder or not? And so forth. And also, of course, an interesting extension in terms of theory would be try to push this envelope to non-Gaussian setup and make our systems also um, systems that are non-linear. That would also be quite interesting because it enables us to consider a larger variety of systems. A lot of systems might not necessarily be linearly described, though you can always approximate them using linear systems. Yeah, so that would be, what we are interested in, pursuing as, generalization of these results into the future. Thank you very much for listening to me. Looking forward to hearing your questions and comments. Please do feel free to reach out to me via my email, farhad.farokhi@unimelb.edu.au. I'll be more than happy to answer any of your questions. Thank you very much.